So, just a minute, there are some crash. Just let me clean the board fast. So, in our last video, we have discussed something about nonlinear system. We discussed closed form of solution for linear system. But now we must know that what we could do to understand a system. There are like here. What is now we will try to means classify nonlinear system in different types of nonlinear system. Like one system is autonomous system. Now here what is meant by autonomous system? I am going to describe it. There are different misconceptions and notions, and I particularly want to aware you that don't get carried away by those misleading concepts available in many of the online videos. It is quite misleading. Like there is a common misconcept or misconception aired everywhere is that if a system is force free, then it is autonomous system. If a system, even if it is a time varying system, then also it is an autonomous system, but that is not the case. So let me try to understand, to elaborate the definition of autonomous system, what I understand by reading the standard literature written by the pioneer of the field like M. Vidyasagar or the other people. So Alberto Isidori. So like them, the pioneering text. What is the notion of autonomy in this pioneering text? Let me try to discuss this. So this was our last day equation. Now, if by any means, if we just write this equation in a form like this, and then if we just drop this one, just a minute, if we just try to drop this ut term from this, yeah, if we just modify the equation like this and just discard the ut term, then it gives a means it may mislead you like this one is a forced system, this one is unforced. Now if this is forced and unforced, first of all, this concept is not correct. It is not correct. It is incorrect to claim the second one is unforced. Obviously, the first one we can see the presence of the actuating signal in our describing equation, that it implies the rate of change of your state or states are being controlled by your external input. However, there is no such explicit mention of input ut in your second equation. So it may gives you an impression that in the second equation there is no such input is present. But if a system is working with a constant input, not constant, rather, not constant, rather a fixed known input, like you know the nature of the input, and that input is like, it can be defined like by means of a function then we can write it like this. Then this present equation, this one can be written like f of u t comma xt, which is structurally identical to our this equation. So don't get confused that I am writing fu, f. It is nothing to get confused. Like if we have that function, we can define a function that is like due to the presence of that constant input, the nature of the states only depend in a particular manner with the state. Like due to the presence of a definite input, a known fixed input to your system, you have a clear notion that how the states are going to change it. So mentioning the state itself can what can I say, that state itself contains all the information, and mentioning u won't add anything extra in your representation. So here we can write it like x dot t is equal to f u t comma xt. So this one basically it can be an unforced system. Obviously you can perceive no input as also a fixed input with magnitude 0, or forced system with there is a scarcity of space. with a fixed input. Fine. Now, let us, with this notion, so we are now considering a system where either the input is completely absent, or even if it is present, then it is fixed, and the nature of the input is fixed and known, so no need to mention it. Now I would like to ask you one question. The way I have described, some of you may develop a notion that I am trying to say it is a case where our system is uncontrollable. Those who those who are acquainted with the term uncontrollable may think that sir is trying to say that the system states are independent of inputs, so due to the application of fixed input, so some of may get confused. So my question is that whether if for a fixed input, if we represent it in this way, then does it imply that our system is an uncontrollable system, or it implies a system that is controllable but it is acting with a fixed known input, and here we can represent everything in terms of time and state. So here we would like to learn two definitions. This system, if this system is independent of t, like this system can be represented as then we can consider it as autonomous system. Independent of time means how the rate of change of states are being governed by the present or past state. It is rather the not past state, the present state. It is this relationship does not contain any time information, or better to say in a single line that rate of change of state is totally independent of time. Fine. Then we call it as autonomous system. Otherwise, this system is an non-autonomous system. Now, another definition we would like to learn, vector, that is x naught, a vector in n-dimensional space is said to be the equilibrium point at time what is happening here, time t is equal to t0 belongs to r plus, or you can write it like this is writing these and these are same. So this we can say x naught is equilibrium if we can write so basically it indicates that if your means this equal to 0 implies what? Or this x dot is equal to 0 means all the rate of change of your state have become 0 when your system somehow reach this. You can visualize vector in n-dimensional space like a point. Like if I want to mention that what is a vector, let me give you one example. If I take a 3-dimensional space, suppose if I take the example of my room, and if I want to have a point here like any point here having magnitude like so basically it is the point. If we draw a corresponding projection here on this line, we will get 3, and accordingly if we just leave this plane here, then we will find that this point is having a projection here 4 and here 3, sorry not 3, 2. So basically, but if you see this 4, 2, 3, we can write it like it is a n-dimensional vector. So if your system in equilibrium means any point in a vector space can be viewed in an n-dimensional vector space can be viewed as a point. Now what is happening here, that in your state space, if it is a 3-dimensional state space, suppose you have something like this. You start from somewhere here and randomly you make a journey, and after reaching this particular point, say any point that is having the characteristics of x naught, your rate of change of states becomes 0. So basically if x1 dot, x2 dot and x3 dot becomes 0, then it implies that for all future time, if there is no rate of change, then there will be no such change in position. Like if you do not change the velocity of a part, means if you there is no velocity exists in a particle, it is 0 velocity, then obviously the displacement of that particle will become 0. So that is a very simple thing. So if now the equilibrium point implies where obviously when Professor Samanta will discuss it in his class, he will obviously discuss many things extra in addition to this. The present purview of the course is not to discuss the essence of equilibrium point. You will get many things, means you will get to know many other advanced concepts in your linear system. Now in this context of equilibrium point, we will try to understand the difference between isolated equilibrium and continuum equilibrium. In addition, we will see that in case of LTI system, linear time invariant system, we have only one equilibrium point for LTI. However, for nonlinear system, we can have even if it is a time invariant, can also have multiple equilibrium point. So let us just try to understand this by means of a simple example. We will study one linear system and one non-linear system side by side, and we will see the existence of. Let us consider an RLC circuit. Okay. So in case of an RLC circuit, let me draw it in a different manner. If you try to write down the equation, you will find if I is the current flowing through the circuit and L or in other way you can write it like this, and L di dt is equal to so also you can side transpose this L to find out this. Now if you consider that all this is an, if it is an LTI circuit means this L, C and R are time invariant, then one thing is very clear that this circuit will, what would be the equilibrium point? First of all, by if we consider the definition of the equilibrium point, then the equilibrium point is when x dot is equal to 0. So when x dot is equal to 0, if we have to consider that as our equilibrium point, so we have to make dvc dt is equal to 0 and di dt is equal to 0. So that condition leads us to a situation divisibility tends to 0 implies I is equal to 0, and therefore if I is equal to 0 is if we put it here, because we can't have divisibility is equal to 0 for any other value of I not is equal to 0 implies divisibility not is equal to 0, therefore violates the means requirement, or means doesn't fit well with the requirement of your equilibrium point. Now you are considering here, if you consider this second one, that means you have no other choice other than considering I is equal to 0. Then if you put I is equal to 0 in here, then what you will get? You have to make di dt is equal to 0 minus Vc by L So basically, it is implying a condition when your capacitor voltage will reach to the means your applied DC voltage, then then it will reach to its equilibrium condition. Now here, uh, this is one condition. Another condition is that, therefore, if we apply now, if we change this this DC voltage by a sinusoidal input, then what would happen? You may pondering upon that. Now anyway, so we have found our equilibrium point. That is very clear. I is equal to 0 and Vc is equal to E. Now, if our definition, by virtue of our definition, if E is a fixed input, fixed node input, then this Vc is constant for a given E. You are not permitted to change your E. As per our the definition we have considered here, before coming to the equilibrium point, we have to consider this form to find out our equilibrium point. So if that is the case, then E has to be a definite known fixed input. So if that is E is definite fixed known input, then you will have end up with this. And if you this Vc, obviously if you make one Vc, then so basically we are having an equilibrium point that is located at your E and I is equal to 0. Now let us introduce some nonlinear element in our circuit. Like, let me redraw this circuit with presence of a tunnel diode. We will connect the diode across this capacitor. And here the diode will be connected this current, let us write this as I, here it is IC, here it is IT. tunnel diode current, the voltage across this diode will be how much? Basically, VC is equal to VC also we can write because they are connected in parallel. Anyway, so and let me draw the diagram, characteristics diagram of tunnel diode. I wish I could take a snapshot of from anywhere. Just let me just wait for a while. Let me see, search whether or not. Now it seems you are feeling a bit suffocated with all this. Let me just give you some numerical values. Numerical values help us to understand subject in a more clear manner. Let us take this example. I am taking it from Hassan Khalil. This is a state model. It is commonly available everywhere. The example numerical value which I am going to take, that is from Hassan Khalil. So here one thing is very clear, that until unless you know this age, it is difficult to find out the system equation. So what I can do, okay, so this is our equation. Now, so we have taken these values from the book of Hassan Khalil, and finally if we take the time in nanosecond, then the equation takes in this form. And also let us take the equation of hx, otherwise we know hx1, we cannot form this one. hx1, as in the book of Hassan Khalil, it is like minus, not minus, it is plus, the last term is plus, it is 83.72 x15, right? So this is the expression I have taken from the book of Hassan Khalil. And our equilibrium point, of course the equilibrium point asks us to reach a point where x1 dot is equal to 0 and x2 dot is equal to 0. So if that is the case, then if x1 dot is equal to 0 and x2 dot is equal to 0, just a minute. Okay, so what we can see here is that for x1 dot is equal to 0 and x2 dot is equal to 0, this will give us a situation. We will have three different combination of x1, x2 that would satisfy our equilibrium point, like x1, x2. First one is will be 0.063, that is x1, the voltage across capacitor, and it is 0.758, that is the inductor current. Then we will having another one, that is 0.285, and another one is having 0.61. The third one is 0.884, and the corresponding x2 value is 0.21. So I have also borrowed, this is as I have borrowed the problem from Hassan Khalil, I would like to borrow the few cards also from that book, because drawing it by means of freehand is not that easy for me. Yes, that would be like just a minute. There is some problem is happening here. Uh, just a minute. Let me try to figure sort this. So I have marked the point here Q1, Q2, Q3. Now one thing it is very interesting to note that if you see in Q1 and Q2 not Q1 and Q2, rather Q1 and Q3, they are located at a region where it is your tunnel diode is exhibiting a characteristics of system having positive resistance value, like the slope of VI curve is positive. However, if you consider the point Q2, there the slope of VI curve is negative. So basically from this we can conclude that here your Q1 and Q3, later on we will also elaborate this why I am having such kind of conclusion, that Q1 and Q3 are stable equilibrium and Q2 is an unstable equilibrium. Your Q2, even the system states momentarily reach Q2, they will get deviated from Q2 and reach either in Q1 or Q3. So basically what is happening here, that suppose if you apply a very small voltage here, then for that you are getting one equilibrium condition, and if you further increase your voltage, then you are getting another equilibrium condition. So this can be viewed as a circuit with two stable equilibrium point, or we can say it is a bistable circuit. In the very early age, people use this tunnel diode as like a what can I say, that a kind of like what is that name of that device, that computer memory, right? So people use this as a computer memory, where that Q1 with a certain voltage level, Q1 stores one, it is like binary, Q1 represents 0 and Q3 represent 1, it is like that, you can view it in that way. You if you just suddenly change the voltage from one to another value, then it will settle to Q3. So this is the situation here, and later on we will further take the example of tunnel diode to elaborate. What is the purpose of my showing you this experiment or this example is that when we are having only LRC series circuit, as we have shown in the previous case, we are having only one equilibrium where inductor current is 0 and capacitor voltage is equal to the external circuit voltage. However, after inserting this tunnel diode in parallel with the capacitor, what we are observing here, instead of 1, now due to introduction of this nonlinear element, we are having three equilibrium point. Obviously 3 isolated equilibrium, they are distinct and identifiable, but in these 3 equilibrium, this is just due to introduction of tunnel diode. Like we can have 3 different voltage of diode, voltage across not diode, voltage across diode is not our state, rather the voltage across capacitor, which is also in other way the voltage across diode, but voltage across capacitor and the inductor current, they are we are having 3 combination of them, so that they make with these three different combinations, they can make sure that rate of change of voltage and rate of change of current become 0. Right? Now we'll see a case of continuous equilibrium. Now we will move to the consider of isolated equilibrium. So when we can have more than one equilibrium, then only the question of isolated equilibrium or continuum of equilibrium will come in the picture. Otherwise, there is no meaning. Like for a linear system, if it is having a single equilibrium, then always it is an isolated equilibrium. So let us take a look on the definition. What do we mean by the notion of isolated equilibrium? We can write that an equilibrium point x naught, better let me write it here, is said to be an isolated if there exists, after the now I am writing there exists, in future I may use this notation also. A neighborhood N0 of x0 in Rn such that so this is the definition of an isolated equilibrium. What it is trying to say, suppose for a given system, say it is a three-dimensional system, you figure out three different or three or two different points in a three-dimensional space. Suppose if you have that much, that many number of equilibrium point. Now after your calculation of equilibrium point is complete, then you form a ball around that equilibrium point. The ball radius can be anything, but it should be greater than 0. Means means ball is, even if it is infinite small, but ball is, there exists a ball and it is means kind of measurable thing. And when you have that ball formed around your equilibrium point, you cannot find, if it is an isolated equilibrium, you cannot find any other equilibrium point exists inside that ball. So obviously the notion of isolated equilibrium point seems it makes impression that all equilibrium point whatever we are getting everywhere is an isolated equilibrium point, but in reality it is not. In a few cases it may be a continuum of equilibrium point. Let me elaborate. Right. So I'm having trouble with this whiteboard. Now we will try to find out or read a theorem on such isolated equilibrium point, that when an equilibrium point is an isolated equilibrium point. So for that, let me write down the equation of the autonomous system first. Not autonomous, sorry, not autonomous. It is like it is not autonomous, rather it is the system that is acting with either no force or a fixed load input operation. So for this system, if we can write or say, let us consider that x naught is an equilibrium point for that system at time t is equal to 0, then we can claim that x naught is an isolated equilibrium if we can see a condition. First of all, let me write. Here it is, this pen tablet makes it very difficult. In class it was quite easy. Anyway, we are writing, or rather defining, this is the definition of A T naught, a new matrix we are defining in this way. So here, what is the intention behind defining this matrix? Can you tell me the dimension of this matrix? Obviously, it is see, it is there like del x, and you are obtaining, you are having an n dimensional vector, and you are obtaining, it is like, if you write it, those who are new to this subject, I can write a first few line for del x, this for them, like the first one will be in this way it is constructed. Now we can write one more thing here, that if this is our AT naught, then if this AT naught, this matrix is non-singular, then X naught is an isolated equilibrium. Actually, in addition to the difficulty of this pen tablet, my mouse is also not working properly. I am having difficulties in just a minute. Okay, so we define A T naught this F is also a vector. So A T naught is a matrix whose elements are computed using this method of partial differentiation and evaluated at a particular point x is equal to x naught. And then we are claiming that if A is non-singular, then non-singular means determinant of A is not is equal to 0, then the equilibrium point is an isolated equilibrium. So how we can prove? In order to do that, we need the notion of norm. Norm is nothing else, means there are different type of norms. For us, it is the Euclidean norm will be sufficient for our present purpose. So norm can be, we can define norm like this is the definition of Euclidean norm for a vector. Well, now, if this is the case, then what we can write that if AT0 is non-singular, then there exists a positive constant C. It is all from matrix theory. We can write it like if there exists like non-singular matrix AT0, it is non-singular, and then we are having and this is valid for x belongs to Rn, right? Now here one thing I forgot to mention, that while writing this, we are considering that this f is means continuously differentiable, and f is at least means the first order partial differentiation of f exists, right? We have different type of variable. Later on we will discuss some function are C1 function, C0 function, C2 function. We will discuss that, like continuous function with 1 degree of differentiability, continuous function with 2 degree of differentiability. We will discuss later. But for the time being, let us consider that f F is what? Our system description started with x dot is equal to f of t comma x comma ut. However, here we are considering a situation that is either experiencing no force from the outside or it is acting with a fixed known input. So in that case, in these two cases with a fixed known input or either no input, we can further simplify the representation of the system equation like x dot is equal to f of t comma xt. Instead of f of t comma xt comma ut, the system that is acting with no input or fixed known input, here there is no need to explicitly mention the ut in your system definition. For those kind of system, we can find out the equilibrium point by solving a equation x dot is equal to 0, that either way imply f of x comma t is f of t comma x is equal to 0. So while solving that f of t comma x is equal to 0, we see that for linear system we can have one equilibrium, for non-linear system we can have multiple equilibrium. Now we are proceeding to the next section when we are claiming that in some case it may happen that instead of having a single isolated equilibrium, we will have a continuum of equilibrium. Now to make it more clear that what is the condition a system must fulfill to have isolated equilibrium, we are proceeding with this claim. First we define the notion of isolated equilibrium, then we are proceeding with this, like we are obtaining a matrix by doing this operation del f del x when t is equal to t0 and x is equal to x naught. So x is equal to x naught implies that all the partial differentiation when you are going to evaluate it, it is evaluated with respect to a particular value of x, that is in x naught. Now we are claiming that the A defined in this way, if this A is non-singular, then our system is having an isolated equilibrium. But now we are trying to prove it. Like we are trying to substantiate that claim, that whatever we have claimed that the A defined in this way, if we find A is non-singular, then we can claim that our equilibrium point is also isolated. So for that, as we have assumed that f of t comma 0 is like f of this function, it is we can just let me just scroll down. Then we can expand it like This f is also vector. Try to write it in bold. Huh? It is becoming a bit means this description, instead of let us write it like where this r t0 comma x is r t0 comma x comprises all the higher order term like second order, third order, all these terms. And here this one, if you notice, then this can be written as, this can be simplified as by the definition of A. We can write it like, fine. Now this one here, or the remaining term, we can have a property. We are assuming that the remaining term satisfies a property like so basically what does this statement, single statement implies from this limiting condition? In a layman language we can understand that this r t0 comma x, that is means shrinking down to 0 at a faster rate than that of the rate by which this norm of x minus x0 approach to 0, this the numerator term, the denominator term approach 0 at a bit slower rate, but the numerator term is approaching 0 at a faster rate when the denominator term is trying to approach 0, and that is why the limit is becoming 0. Now if that is the case, then here what we can write, if you see this equation, now you, oh God, this is pathetic. Here this first term, consider this first term. What is this? Don't you think by virtue of the definition of equilibrium point, this is also is equal to 0? Because what we define, that x dot is equal to 0 at x0, and when you will get x0, x0 is basically the value of x t0, x at t0. So basically t0 x0, when you hit it like this, now one question can be raised, that sir, why if f t0 x0 is 0, then why are you doing so much wrestling with ft0 comma x? Because ft0 comma x and ft0 x0, it is like whenever you are at t0, then obviously you are at x0. But if this question comes in your mind, I would like to remind you that from where we started this discussion, or what is the genesis of this all these processes. We are investigating whether we can have a continuum of equilibrium. Try to understand the beauty of the term. Like you are having equilibrium, one equilibrium, another equilibrium, another equilibrium, another equilibrium. All these are like inseparable. So at time t0, if you reach to a inseparable this combination of 3 or 4 inseparable points, it is very difficult whether you are exactly at x0 or you are at somewhere that is very close to x0, means it is inseparable, as I said. So if that is the case, then obviously even if you make it 0, you can't claim this one is 0, because our equilibrium point is x0. Now we will see that what we are getting here, that we are not writing here x, because x is a it can be viewed as a it can be anything in that continuum point, means in that space position where your all these are means it may happen that all the equilibrium points are clubbed together. We are not at all sure of it as of now. We will prove it that there cannot exist any other point that satisfies the condition of equilibrium other than this x0. We will prove it. But for proving that, I need to scroll, and for that I need to now if that is the case, let us pick a positive number d greater than 0 and c greater than 0. So if d greater than 0 and c greater than 0, what we will do with this d and c? We are going to make a further claim that d and c are selected in such a way that let me write it clearly. Give me some time. The norm of, yeah, it is there. So let me copy it. Here, at that time I forgot to write the norm expression for the second means numerator. Numerator is also taking, we are taking second norm. Everywhere it is second norm. Don't forget this. So we have selected C and D in such a manner that this becomes for all so C and D are selected in such a way that they are satisfying this means condition that whenever x minus x naught uh, 2 norm of this is less than d, then the remaining term divided by the norm is less than c by 2. Now this what we are actually trying to prove that in the neighborhood there would not exist any equilibrium point other than x naught, right? Just let me take some time to go to main page. We found out this ft naught comma x is equal to at naught x minus x naught plus rt naught comma x, and also in addition we have defined our two positive real numbers c and d such that these are this definition second norm of r by second norm of x minus x naught is less than is equal to c whenever the value x minus x naught norm of x minus x naught here also I should write the 2 is less than is equal to d. Oh, no, not less than is equal to here, yeah, less than. It is not less than is equal to. It is just less than. Like what is my objective of defining all these things? Because here I am going to define a neighborhood of x naught, neighborhood of x naught based on this d. How can we define a neighborhood of x naught? We will define a neighborhood n contains all x such that obviously it belongs to Rn, we cannot go beyond Rn, such that this is the way we should define our neighborhood, right? So we have defined our neighborhood. Now with this definition of neighborhood, it is D actually. I am getting it. This is the neighborhood of our x naught. We have defined such that the neighborhood you can view it as a ball, right? And what is the radius of the ball? The radius of the ball is less than d. Like if let us have a ball, outer ball d, if we go beyond that ball, if we move away from x naught and if we move beyond that ball defined by the radius d with its center at x naught, we will move out of this neighborhood, right? Now if that is the case, then what is our claim? All this mumbo jumbo starts from the point that we are trying to establish that this is an isolated equilibrium point. So let us consider that a point, any point x that belongs to that neighborhood n, but it is not equal to x naught. So if that is the case, then we can write then we can write that let me write what we can write, that same thing. But we are taking norm of both left hand side and right hand side. Now, the interesting property of norm is like they always satisfy triangle inequality. So, we can write it is like this whole thing so if that is the case, then we can write now see what is our this RT naught x, this maximum value of this is how much? Max of this is c by 2, right? And what is our AT naught x minus x naught non? We can write it like this is now here one thing if I forgot to mention that here the C and D how we are assuming, one thing you must note that let me go back to the previous page, otherwise I think because I am having the paper from which I am writing. Here, see, yeah. So here, see, this is the point I have written. So the way we have defined C and D, now see the beauty, what I am trying to establish here. Yeah, this is the one. Now see, where is that second part? Yeah, here the way we have defined C greater than 0, D greater than 0 such that this is less than is equal to C whenever this is greater than D, sorry, less than D. So it is less than is equal to C, and that C is coming from that. There is no hun because a t naught is non-singular. Now if this is C, so from that we can write that yes, here now we can write. So this is a t naught x can be written as like this. So here we can have this. Just a minute. Let me just check once that whether I have made any mistake while writing that, because otherwise you people will get confused. Well, it is my fault. Had I written this in here, then you would not have to run anywhere. Okay, so now just a minute. Yeah. So here what we can see is so hence prove that right. So here f of t0 comma x 2 greater than 0. So what does this imply? That is, so therefore the n no other equilibrium than x naught at p is equal to p0. So once again, let me just quickly revise it what I just try to do with all this. Yeah, here we have defined this, and also if AT0 is non-singular, then by virtue of matrix property we can show that yes, if AT0 is non-singular, then we will have an isolated equilibrium. So then we define the norm. Then what we did, we claim that we will have a point at naught x such that c for all c greater than 0. Then we proceed to the next section where we claim it is like that. Then we are getting inside our equilibrium there doesn't exist any, sorry, not equilibrium, inside the neighborhood of the equilibrium there doesn't exist any other equilibrium point than the main equilibrium.